Okay, so in the last video in this series, I discussed should just let me resize this here because I'm going to do some writing. Yeah, so I discussed the MPC component of the TD-MPC method. And this is what's done at rollout when the robot's actually got to do the task. And it relied on a number of neural networks to make certain predictions in order for the machinery of MPC, and that is the cross entropy method, which is the underlying algorithm, to work. So just to remind you, those were the dynamics model, which takes in a state at a certain time and an action that you try to make the robot do at that time, and that produces as the next time step state. There's the reward model, which takes in a state and an action and tries to predict what the reward will be for that. And there was the state action value function, or the Q function, which is takes in a state and an action again and tries to estimate what will be the future return. So the sum of all rewards from all steps of the episode from now and thereafter until the end of the episode. Now, there are two other neural networks that I didn't mention when I spoke about MPC. They just weren't necessary to get across to you how the MPC works here. But they are part of the TD-MPC. So there's the observation encoder or state encoder. So that takes whatever was in the state, so maybe images of the scene, joint angles of the robot, and it embeds that into a latent representation. This is an abstract representation that's not human readable or anything like that. And we'll see a little bit more about how that's trained soon. And actually, I'm going to replace all of these S's up here with Z's because that's what's actually happening in TD-MPC. They're not feeding the state directly into these models here. Now, there are two really good reasons for doing this. One is speed. So you have potentially something that's quite high dimensional as the state here. So you could have like actual, images like 240 by 240 pixels or bigger that you need to encode down to like a lower dimension. And remember from before that when we were going to take like a sequence of actions, right, over a horizon and try to simulate the dynamics using the dynamics model, we were going to have to feed in the state at each step. So it actually makes a lot. Oh, and by the way, this should be a Z here as well. And it makes a lot more sense to operate in this latent dimensions, which is much lower dimensional. And so there's much less processing required here. The other reason is that this model here does all the work of trying to abstract away the irrelevant parts of the observation and focus on only what's relevant, and then pass that to the dynamics, reward, and state action value function. So we'll see a lot more about how that works in a moment when we look at the training, like what we're actually optimizing in terms of objectives. Now, there's one more model, which is the policy model. It takes in a state and it outputs an action. And just a quick side note before I continue, this is edited in after because I realized I've raised a big question here because in the previous video, we learned about MPC and how we can use that to end up getting like an action trajectory to run on our robot. But now I've introduced this policy network which predicts actions. So what's the purpose of this? Well, if you recall, when we run the cross entropy method for MPC, we start off with drawing some number of random samples from a Gaussian distribution to create like proposals for action trajectories. And then the question is, why not learn a policy network as well at the same time and add to those 100 samples some samples which we generate using this policy network. And if those are good, then they'll get promoted to the next iteration of the cross-entropy method because they'll be among the elites. And if they're not, fine, we're just using the vanilla cross-entropy method. So that's what this policy network is for. Right, so now speaking of the data set, let's just understand what that looks like. there are two ways that the data set comes about here. One is you've either pre-recorded some demonstrations, that's actually an optional part, and then the actual part that's in the TD-MPC training loop is every now and then, in between training, like network updates, there's a step where the robot actually runs rollouts using MPC with these neural networks here, and we record that as we go. So I've just drawn what the data set kind of looks like. You have a series of states, you have a series of actions that led to those states and the rewards. And in order to build like a training batch, like one of the items of the batch involves taking a slice over a certain horizon of this data here. So if you recall from my last video, I used the parameter horizon equals 5. We'll stick with that for now. And we'll take a slice of this data set. It will take 6 elements in a row, actually, not just 5, and you'll see why that is the case in a moment. So we'll take this slice right here, for instance. Okay, so now I'm going to go through, how we feed these into the neural networks and what the training losses are. And there's going to be a lot going on here. And for me, when I read this was a bit like playing whack-a-mole, in that every time I came to understand one concept, I'd forget the previous one because there's just so many things happening. So don't get too bogged down in the details. Just try to follow along, and then when you actually need the details, you can go and consult the code or the paper. And definitely this is the approach I take, because even making this video, and I've actually re-implemented TD-MPC myself, I still forget and I have to check the code. Okay, so I'll take a graphical approach towards this here. So we'll start with our first state that we've gotten from our batch, right? And what we're going to do is we're going to pass that through the encoder, right? And that's going to give us a predicted latent embedding. I'll put a little hat here just to emphasize that it came from a neural network. So that's Z1. And then what we're going to do with that, well, there are many things we're going to do, and they don't have to be in this order necessarily. But one of the things we could do is pass it through the policy network. So we pass that through the policy network, and that predicts an action at time 1. And now this already gives us our first loss, because we can compute some sort of regression loss. So I'm just going to put L2 loss here between the predicted action and the action from the data set. Okay, but just pause for a second. I have a little side note. I lied about this policy network loss being this simple. It's not a straight regression loss. And the reason I lied is because it's actually more complicated than that. And talking about it just might get in the way of us understanding the rest of the machinery here. On top of that, different flavors of TD-MPC do this differently. But it all revolves around one main idea, I'd say. So when we're doing rollouts with this robot, remember we're doing rollouts with the MPC, and MPC relies on sampling from a Gaussian distribution, and there's noise. There's noise when you do that. So you won't necessarily get the optimal sequence of actions. And this is important. It's part of the exploration versus exploitation dilemma of RL. We add this noise, we inject this noise on purpose so that we can do more exploration. So the trajectories that we gather in this data set here, in the online data set for training, aren't necessarily going to contain the optimal action. So why would it make sense to regress towards actions which are not necessarily optimal? So we need to do the regression in a kind of informed manner, where it's informed by our understanding of how good that action is. And our understanding of how good that action is in TD-MPC comes from the Q network. So this was the network that takes in as input the state and the action and gives you an estimate for the future return of the whole episode. So in TD-MPC, the idea is to pass the action to the Q network, and what you end up trying to do is maximize the output of the Q network. It's probably more nuanced than that. You should look at the paper. In another flavor of TD-MPC, which is the one I actually implemented in Hugging Faces the Robot, they do what's called advantage weighted regression. So each action is weighted by how good we think it is. And how good we think it is based on the Q network and also another V network, which I won't get into details right now. So yeah, that's the gist of why this is more complicated than I actually said. And I hope that you don't get too bogged down in it and you let it go for now and you just assume it's a straight regression. You can come back to that later. The other thing we can do is take the reward model, which will take in the state or the latent embedding of the state, and also the action from the actual data set. So I'm going to put that somewhere here. Action 1. And it's going to output a prediction for the reward at time step 2. And we can look at the mean square error, for example, but there are other losses we could use, between that and the reward from the actual data set. The next thing we can do is we can take the dynamics model, which is also going to take in action 1 from the data set, and also the embedding of the state. And it's going to output Z2. And I'm going to give this a double hat because I can't think of better notation, and you'll see why I gave it a double hat in a moment. But just think of it as, it's the result of 2 neural networks worth of prediction. So we can also take state 2 from the data set now, pass it through the encoder, and get Z single hat 2. So, and what we can compute now is a regression loss of sorts between Z double hat 2 and Z hat 2, right? And so this is called the consistency loss because we're making sure that encoding state 1 and using the dynamics model and getting to Z2, or encoding state 2 to get to Z2 gives you the same thing, right? And also, I'm not going to draw it again, but from here, we can do just as we've done here. We can use the policy to predict the action, and we can predict the reward with the reward model. And going forward, we can just do the same thing for Z3, Z4, Z5, and that's the horizon, but also Z6, because we need to compute the consistency loss still. That's why, so remember before I said the horizon was 5, we took a slice of 6. So this is the horizon that we care about in terms of like the action horizon, but we also need to look at the last state and compute the consistency loss for that. And I want to emphasize again at this point that the policy model and the reward model are applied to each of these stages, except for the last one here. But up to here, these models are applied. And the other thing that you should notice from this is we're reusing the dynamics model in between each of these steps. So we're using it auto-regressively. And when we do backpropagation, it's kind of like the RNN scenario where we do backpropagation through time. I'm just editing this part in after completing the video because I realized I forgot to mention something quite interesting and insightful relating to the state encoder. And well, okay, so to get there, let's ask ourselves a question first. If we just look at the consistency loss alone, why is it that the state encoder doesn't learn to predict zeros all the time? Because if it predicts zeros, then there's zeros here, and then the loss will be 0. And that's how you minimize the loss. And the reason is that actually the reward estimator and the policy network both rely on the Z containing at least the information required to predict those quantities. Okay, and now you may notice that I've glossed over how we train the Q network here because it's not anywhere in this diagram. The reason I did that is because the diagram is complicated enough as it is. And before I talk about that, I just want to take a quick detour into temporal difference learning, which is the TD part of TD-MPC. I'm not going to try to give a full course on TD learning right now, but I'm just going to try to give you my really just intuitive understanding of it. it's going to be a very qualitative understanding of it, and there's plenty of resources you can look at to understand properly and in a more rigorous and formal manner. So before I spoke about in the previous video, I had this this 2D world where this is a wall, and there was an agent and a goal region that the agent had to get to succeed. And I said, okay, well, let's give minus 100 reward for hitting the wall, plus 100 reward for getting to the goal. And we'll also do -1 for every time step as a kind of punishment for taking time to do the task. So it's better to do this than it is to do this, because this takes longer. And also, just to make this a bit easier, we'll discretize. So this is not a continuous space now. Let's just use these little grid squares here as like discrete states, and the agent can move left, right, up, or down. So in order for an RL agent to learn how to do this task properly, first of all, it needs to even discover that there's a reward here. And if it's moving around the space randomly, this could take quite some time. But let's assume that eventually it happens to chance upon the reward. So I've just zoomed in a little bit here, because now I've drawn a little cell there where the goal was, and I put 100 on it. And I've said, okay, well, the value of this state is clearly 100 because I get a reward of 100 for being in it, and the episode terminates. So the sum of the rewards till the end of the episode is 100. And now I can look at the state next to it, and based on my experience, I can ask myself a question, which is, okay, I'm going to break this up into 4 quadrants. I'm going to zoom way in for this. Actually, that's as far as I can go, unfortunately. And based on my experience, if I went left from here, I ended up going to the goal state. So I can say that the value of going left in this state here is 99. Why? Because I take a -1 hit for executing an action for a time step. That's the punishment. But then I get 100 as the reward, and then the episode terminates. I can imagine that I have also done this exploration from this direction as well. And so this little quadrant here is 99. And I can imagine that I've done it from this cell as well. And going left, well, let's figure it out. Basically, the value of being here is 99. And so if I go left from this cell here, I take a hit of -1, and then the value is 99. So the value of being here and taking the left action is 98. And if we go back to this first cell that I drew here, the value of going up is, you can guess it, it's 97, right? The value of going down by the symmetry is 97, and of going right, I suppose you could do that exercise yourself. But you can see here that around this terminal state here, I'm kind of like doing a backfilling exercise. And if I do this enough, I can end up back to the starting position of the agent. So loosely speaking, and I really mean very loosely speaking, the repeated application of this backfilling operation is TD learning. So, you start off with a grid of zeros everywhere for your estimate for the value of each state action pair. And you do this exercise of moving, seeing what reward you get, and then updating your current estimate for the value based on the reward you got and the estimate for your value of the next cell. So to show you how that works, let's add another cell here, and let's put zeros everywhere in it. And let's just talk through what we would do to update the estimate. We would do something like, well, okay, if our experience shows us that if we move left from here, we get a reward of -1. And we can also see, because we already know that the best value that I get out of being in this cell is 99. Then I can say, well, it's 99 -1, or the reward. It's the reward plus the value of the next state, the maximum possible value of the next state, right? And so the answer would be 98. And my rub is not small enough, so I'll just turn this into an 8 and put a 9 there. Yeah, there we are. So how do we just, let's just write that formulaically. So let's just do that exercise again. So I'll reset this all to zeros. Okay, and so we'll say this is time t. We're going to like do the action of trying to move left, and we'll end up here at time t plus 1, right? And we can ask ourselves, based on what we learn, what should we update to in a perfect world? Well, we have the reward. We need to consider the reward, which is going to be -1. And we need to consider the best case scenario for once we're in this state. If we do the best action we can possibly do, what's the value? And that's 99. So we can write that down that as maximum of all actions q s of t plus 1, st plus 1, and action is now a variable that we're trying to maximize over. So this is the TD target. And yeah, so we can compute this. This is -1 and this is plus 99, so it's 98. 98 is what we came with before when we did the exercise. Also, we can think about the TD error. So if this is the target, then the error is this minus our current estimate of the value of this state, which is 0, but written down more generally, it's ST AT, right? That's our current estimate of this of the value of this state and action, right? So then the update rule would be, if this is the error, the update rule will be is take my current estimate and update that to be my current estimate plus the TD error. And actually, we're going to put an alpha here, which is a learning rate. And we're going to make that less than 1. And the reason that we make that alpha less than 1, and we can't just do this update straight away, is because we don't know that this estimate here, 99, is correct. And we're bootstrapping this from the start, where none of our estimates are correct. They're definitely very wrong. So taking massive steps in potentially the wrong direction could make the training quite unstable. So we want to take smaller steps. I think it's a similar concept to why stochastic gradient descent works in neural network optimization. But I also think that I would suggest you look at a textbook or a proper resource to understand the theory behind why this is supposed to converge. Right, so I've taken quite some liberties in glossing over details, and hopefully I haven't been inaccurate with anything. But that in a nutshell is the TD learning update. We went down a bit of a rabbit hole for me to explain that to you, but there are 2 reasons I wanted to explain that in this video. One is I wanted you to understand then how the Q network's loss function works, which I'm about to explain in just a moment. But the other reason is because it helped me build an intuition of how how this model learns, and helped me kind of debug and understand what was going on in my actual experiments. So here I have a setup where I have this blue cube that needs to be pushed to a goal region. Right, that's the task by this robot arm. And the way that I set up the reward structure is that there's a large positive reward for the cube going into the goal region. And also I have a segmentation algorithm which could segment out the cube. It's just a very basic one. Just look for blue in the scene. And I found the distance between the cube and the goal region, and I used that as a reward signal. The problem was, though, that I didn't have a computer vision module for detecting the gripper. And I decided not to have that computer vision module because it was complicated for a variety of reasons. But what it meant was it added complication to my reinforcement learning, which is that if the cube starts here and the arm starts all the way over here, there's no reward signal anywhere until the arm hits the cube. So we have to just chance upon the cube at some point. And then that whole TD learning updates and backfilling will eventually fill out the map in this space of what the value is of each state and action. But that will take a long time, especially with this like real life setup where I have to sit next to it and babysit it the whole time. So I did something called curriculum learning. And the only reason I was able to do this again is because I understood how the TD learning updates worked, where at the beginning of training, I always start the arm near the cube. And that means that, yeah, even if the arm's doing random stuff, it's going to accidentally hit the cube to the left. And it's going to discover, hey, moving the cube to the left is a good thing. And then once I'm confident that's working well, then I start the arm a bit further away from the cube. And even though there's no reward signal for moving left, at least there's a region here where it's known that the value for moving further left is high. So the TD learning algorithm can bootstrap off of that and update the value here based on that. So after a little bit of training, what you end up seeing is that the arm has a preference of, even though there's no direct, like explicit reward signal, it has a preference to move left here. And then it hits the cube and there's a reward signal, right? And you just keep doing that. You move the arm further and further away as it conceptually fills in this map of the value function. I would actually love to plot out a heat map in future experiments to see that actually happening. But I can say from my experience doing this that I could kind of see it happening, because I could see that the arm would eventually learn to, starting here, move left, right? Following the gradient of that value map. Right, so now we're ready to talk about how we're optimizing the Q network. And so the TD arrow tells us that we're trying to push the outputs of the network towards this target here. So for the loss, we're going to take the mean square error between the Q network applied to so we're going to do this separately for each of these states, but I'll just pick Z hat 1 as the first example, right? And the action I'm going to put here is action 1 from the data set, right? So this is the output of my neural network, and the target I'm regressing to is the reward from the data set. And remember, this is R2 because action 1 applied to state 1 gives us reward 2. And now here's where it gets tricky. And I don't want you to get too bogged down in the details, because different flavors of TD-MPC do this differently. But so this expression here, maximum overall possible actions of the Q network, it's not feasible to actually try all possible actions and optimize for that. So what do? Well, one variation of it is to take the Q network. We're going to take in the successor state, Z hat 2. Now, which action do we put in here? Well, supposedly this policy model that we're optimizing is supposed to give us the best possible action in any state. So we're going to use that to give us an action. So we'll apply that to Z hat 2 as well. Right, and this is kind of what they do in TD-MPC. And I say kind of because there are more details, and I'll go through them in a moment. But before I do that, again, the disclaimer is don't get bogged down in it, because then if you look at another flavor of TD-MPC, it'll do it differently. I mean, just the most important thing is you remember that we're trying to regress towards this TD target, and there are different methods for estimating this quantity here. So some of the details here. One is that we use, well, actually, probably in all implementations, we're going to use stop grad here because this is a target, and we don't actually want to update the weights based on this. We just want to update the weights based on this forward pass here. And another detail is actually we don't use the Q networks as is. We use a exponential moving average of the neural network's weights over the training. So I think there may be proper proofs for why this is a good thing to do, and many good reasons. But the one I can think of right now that I've heard before is that it gives you a more stable target to regress towards. So that makes the neural network training more stable. And then there's also the implementation that I coded up in Hugging Faces project, which comes from another paper, another flavor of TD-MPC, which does this quite differently. Actually, I'm not going to go into it, but I'll leave a link in the description for that paper. Okay, so that is pretty much everything you need to know for now in terms of what it looks like to grab an item from the data set, forward pass it through the neural networks and compute losses. Now I'm just going to zoom out a bit and just kind of show you how the whole training loop looks. And I'm going to talk about the variation that we do in Hugging Faces, the robot project, which starts off with a pre-training phase where we have offline training data. And the paper, by the way, I know I'm going to put it in the description, but I'll tell you what it is right now as well. Fine-tuning offline world models. So the first thing you do is you gather a bunch of data offline, and by offline, it just means you gather it prior to doing the training, and then you do your typical training loop where you grab a batch from the data loader and you pass it forward pass through all the neural networks, compute these losses, and do the backward propagation and gradient update step. Now, there is something that threw me off the first time I tried this with my own data set. So, I built a data set where, and I'm just going to enlarge this again, where I was pushing this cube back and forth between the goal regions, and I was doing a really good job of it, the same you would with like a standard imitation learning model. And then I trained with that, and then I decided to see what the performance of the model was, and it was garbage. And this is the counterintuitive bit if you're coming from imitation learning, because you think that if you give it good data, it should learn the policy and do a good job. But there's a whole other aspect here, which is the world model and understanding the value function throughout the state action space. So what was happening was when I ran this and then I finished training the offline part, is I'd set the arm here and I'd start the model running, and the arm would just whack the table, or it would go up. And these two were out of bounds conditions for me, which would give a large negative reward. So the arm would always just do something crazy and wouldn't move towards the cube. And the reason is because I'd not given it any bad data. So I'd not shown the model what it looks like to fail. And remember how the MPC works at inference time. We try out a bunch of different action trajectories, and we try to see which one is the best action trajectory. But how can we know that it is better to move towards the cube and push it to the right than it is to go and do some other crazy thing, if we actually have never seen that other crazy thing happen and we've never seen the consequences of that? So this is totally different from the paradigm of imitation learning I was used to. And so then there's the online training loop, which is a bit different. So we have this offline data set. And then what we have to have is like an online buffer of some capacity, right? Where this is empty at first, and then after we've done the offline portion of the training, we run, say, for example, 20 rollouts of the robot. We make it try to do the task 20 times, and we record that each time. And that fills up part of the buffer. And then we do more of the regular training loop, and that samples somehow with some strategy from both the offline dataset and the online buffer, or maybe just the online buffer. And then after some number of steps, which is the hyperparameter we set, we do a bunch more rollouts, and that fills up the buffer even more. Eventually the buffer gets full, and then we start like pushing things out of the buffer, either in some sort of strategic way where we pick what to push out of the buffer, or it just whatever was put in there first will come out first. And then just to like give you like what my experience was with this is, yeah, so the first time I collected data, this arm just kept whacking the table. And it's occasionally accidentally whacking the cube to the right a little bit or moving left. And then as soon as I did my first round of training with that data in online buffer, the behavior changed. Instead of whacking the table, it started going up and going out of bounds upways. So it had clearly very quickly learned that whacking the table is a bad thing to do. But then it went and tried something else that was not the thing that I wanted it to do. And then after a few more iterations of this like online data gathering, I started to see this, right? Just like a nudging the cube to the right, but then hitting the table, or nudging the cube to the right, and then going up. And then after maybe half an hour of training, I got to see my first success where it pushed the cube all the way to the right. But sometimes it would, hit the table along the way or move up along the way. And eventually, it took several hours before it eventually got to kind of 80% success rate. Sorry, I'm showing you with my hand here, but there are other videos that I posted which show this, and I forgot to enlarge this. So 80% success rate looked like kind of like, yeah, it was pushing the cube across and starting and pushing the cube across. But sometimes if it failed to push the cube across kind of like this, and the cube ended up here, and the arm started here, it was hard for it to figure out that it had to move up and pull the cube back in. And after some time, it was even able to learn that kind of behavior, but it took quite a lot of training. So yeah, that's it for TD-MPC. I tried to keep from going into unnecessary details, and I'm sure I did go into some, but the idea was to get the core concepts across because the details are something that I always forget anyway, no matter how many times I implement it. And when I come back to implement it, I can go into them and quickly recall them. For me, the most interesting concepts here were some of the interesting loss functions. So the consistency loss for learning the latent space for the states, and the TD learning part of it. So I knew about TD learning before, but it's always nice to get a reminder of it. And I enjoyed trying to come up with a way to describe it and explain it to you. And then the online training loop and how that works, and the realization I had, which was that it's not like imitation. So the offline training part is not like imitation learning, in that once you're done training, you're not going to have a model which does what you want it to do, because you still need to learn the value function. All right, so thanks very much for your time, and I really hope you enjoyed it and it was useful for you.